Era necesario. Sí, perdón, entonces a lo mejor yo creo que ahora
Okay, so welcome everybody, for the people from the department. As probably you observed, I'm not Jose. He's not here today, so I'm in charge of presenting the colloquium. And well, actually, it's a pleasure to me, for me to introduce Xavier Fernández-Real, who will give the colloquium Premio Rubio de Francia. So let me just say some words about Xavi. Xavi did his PhD in the Swiss Federal Institute of Technology, that we call ETH, in Zurich, under the supervision of Alessio Figali. He finished in 2020. And then he went to the Swiss Federal Institute of Technology, Lausanne, EPFL, where he has occupied different positions. He has been a postdoctoral researcher, a Bernoulli instructor, and recently Ambizione Fellow, I think is the name, okay, which is a position attached to a very prestigious grant awarded by the Swiss National Science Foundation. As you probably know, Xavier works in the field of partial differential equations, where he has important contributions, especially in several areas, especially in elliptic and parabolic equations, transport equations, free boundary problems, integral differential equations, and more things. His production already includes over 20 research papers and 2 books. His work has been recognized in many ways. Let me just mention some of them. He's been awarded the ETH medal for outstanding doctoral thesis, the prize Vicente Caselles of the Spanish Royal Mathematical Society, both in 2021, the Ferran Sunyer y Balaguer Prize for one of his books in 2023. As well as the Antonio Valle Prize, awarded to mathematicians under 34 years of age by the Spanish Society of Applied Mathematics. This also in 2023. And very recently, he has been awarded he's the winner of this year's José Luis Rubio de Francia Prize, which is the reason why he's here today. So I'm very happy to have you here. And he will talk about the fractional obstacle problem, so please.
Thank you very much, Maria, for a very exhaustive and very nice presentation. I thank also the department. It's probably the department I've visited more often in my career, so I'm very grateful. And also because the fact that the Rubio de Francia Prize is partially sponsored by you, so thank you very much. And I'm going to talk about the fractional obstacle problem. Maybe a couple of, let me put the timer. A couple of warnings I usually do before starting a talk. One warning is that I usually speak very fast, and usually I try to stop myself, like now, but if I get too excited about what I'm explaining, then things change, but I try to compensate for that by repeating myself a lot. So if you want to stop me or ask a question, please feel free, but hopefully the density of information I'm giving you is not too high. And second warning, the talk, it's kind of like a wave. It will increase and decrease in difficulty. I understand that not everyone is an analyst, but I will try to introduce the topic, but at some point I will just do a steep increase in difficulty and then go back. There's many places to pick up again. So the talk is designed like that. If at some point you are bored of my talk, myself, you want whatever, you can disconnect and you can connect again in the future. So just don't give up. And so let me start. So the talk is the fractional obstacle problem, which is a topic very dear to me. It's mostly the topic I did during my PhD thesis. And what I'm going to do is I'm going to explain what this is. Basically, I will start with what's the obstacle problem, why do we care about the fractional part, but because it's not too dense. And hopefully by the end, I will be able to introduce some recent results on things that we have done in the last 3 years. So, let's start. So, obstacle problems are part of a larger family of problems that are called free boundary problems in PDE. And basically, they are problems, free boundary problems, where there is an appearance of an interface. Free boundary problems are typically used as models in physics, biology, economy, and they usually appear when you are trying to model an extra effect of the medium where you are that provides different properties to the same substance according to what's happening. I will be more clear now. And this gives rise to the appearance of interfaces. For example, when you have ice that is melting into water, you have the same substance, but there's two completely different behaviors according to the temperature of the water. Or when you, this more generally, if you have any crystal turning into liquid, same is going to happen. Or when you have an option, buying versus selling an asset in the stock market, it's the same thing, but according to the value, there's different behaviors. Or in biology, having an active versus an inactive population in a region. It's the same concept, but there's completely different behaviors according to what's the value of the density of the species at a certain point. So, these are free boundary problems in general. As I said, they appear in many places. The most common example is the first thing I said, which is ice melting into water, which comes from Stefan problem, which is now very classical, and I'm not going to go deep into it, just to say that it's a model. So the Stefan problem can be reformulated in terms of the obstacle problem, which is the first free boundary problem I want to talk about, and it's probably the easiest one to explain, because it's very easy to visualize what I'm trying to do. So basically, there's many formulations. What I'm going to do first is try to introduce the formulations, and since they are different, hopefully each of you can find one of the formulations closer to you so that it's easier to understand. Okay, so if you don't understand one, just as I said before, just disconnect, wait for the next one. The first intuitive explanation is this. What I'm trying to do is, I will have a domain, I will have some smooth function, phi. Typically, I would think of it as a concave function that maybe goes to 0 to infinity, so it's not concave everywhere, but some global, I don't care about its regularity, so assume it's infinity. And typically, I have some elliptic operator that sometimes will come from an energy, but it's just something that describes what's the equilibrium state of the membrane that I want to put above. So what I do now is I try to put above this phi a membrane whose equilibrium state will be given by some operator. So I'm trying to minimize some energy, then I can decide which energy I want to minimize. Typically, you want to minimize, for example, the area. No? You want to put some boundary datum and you want to minimize the area. You just put some boundary datum, you put the membrane above the obstacle, and the membrane is going to touch in a certain region, and in another region, it's going to be detached from the obstacle. And a priori, you don't know. You don't know where it's going to touch, you don't know where it's going to be above the obstacle, you don't know what do you expect the membrane, how smooth do you expect the membrane to be, you don't know anything. This is called the obstacle problem. Now I have to give more what's L, what's everything. But as a general idea, this is the obstacle problem. And you see this is a free boundary problem, free boundary problems, because there's going to be a region where the membrane touches the obstacle, there's going to be a region where the membrane doesn't touch the obstacle. The region where the membrane touches the obstacle, in the domain space, it's called the contact set. And a priori, it's an unknown of the problem. I don't know where the contact set is going to be. It's part of the question. It's where is this touching, if I'm just minimizing the energy. This set is an unknown. It's called the contact set. Its boundary, that I don't know, it's free. It's the free boundary. So this is a free boundary problem. And what I want to study is two things. What's the regularity of my minimizer, or my membrane? I don't want to call it minimizer because it's not always a minimizer. The second question is, what can I say about the touching region? From a PDE point of view, this thing I formulated a bit hand-waving. has a PD associated to it, has a system of PDs, which is not so important, but if you care about it, I can show the PD. So basically, I'm looking for a function, u, that's going to be above the obstacle. U is going to satisfy that. If you think of L, if you want, you can think of L as the Laplacian, or minus the Laplacian. When L is the Laplacian, the function is going to be harmonic whenever it's not touching the obstacle. It's because locally, if you don't touch the obstacle, it's like if the obstacle is not there, and if I'm minimizing locally an energy, I'm going to be harmonic. But in general, you could touch the obstacle, so it could be that I'm at a touching point, and then I can only modify the function in one direction. So in general, I'm super harmonic. So I only have one direction. And this is a PD. This determines uniquely the solution once you fix the boundary datum. And sometimes people call the obstacle problem to that PD there, which is after a change of variables, you subtract the obstacle, you assume that the Laplacian is -1, whatever. It's not so important because I'm not going to deal with that. But sometimes people call it that, just in case if you want to compare to anything you might not know. This is a semi-linear PD. You look at Laplacian U equals the characteristic function of the positivity set of U. And as before, you want to understand what's the set, just this PD. The solution to this PD will give rise to a set where U is 0 and a set where U is positive. But you don't know a priori what it is. And you wonder what's the shape of this set. Is it nice? Is it not nice? Can it be an arbitrary thing? You see, even if you knew that the function U was C infinity and the obstacle was C infinity, the contact between two C infinity functions can be anything. So a priori, it could be a fractal set. Okay, so this is probably the most classical free boundary problem. And as I said, the contact set is the region where U is equal to the obstacle, and its boundary is called the free boundary. So this was the hand wave interpretation, or the PD interpretation. I gave you a PD, I told you this is the obstacle problem. There's another interpretation, which is the variational interpretation, which is more related to my first explanation, which is the obstacle problem can be recovered as a variational problem. In this case, you have an energy. You don't always need to have an energy to have an obstacle problem, but if you have an energy, you can define an obstacle problem. So you can have an energy, and what you try to do is you try to minimize whatever energy you're trying to minimize. Think now the Dirichlet energy, if you want, and you add a further convex restriction to the set of competitors you can take. So you don't take arbitrary competitors in whatever energy space you're doing. You add the restriction that the competitor needs to be above the given obstacle. Okay? And then your choice of energy will give different types of obstacle problems. For example, if you choose the energy, the Dirichlet energy, the H1 norm, the energy, the Dirichlet energy, the H1 norm, semi-norm, then you can take your set of functions that you are taking is the H1 functions with a prescribed boundary datum G. Then this is called the classical obstacle problem. In this case, in the previous setting, you had L equals to minus the Laplacian. If you take as the energy the fractional energy, so the fractional HS energy, which means that you take, so here the semi-norm, the fractional HS energy, which means that your set of A's is going to be, again, with boundary external datum G, W A's S2 functions, then you get what's called the fractional obstacle problem. Now, this doesn't need to tell you anything now, because I haven't defined fractional energies, and I understand that not everyone is comfortable with fractional solid spaces. But basically, this fractional energy, you can think of it as an interpolation between H1 and L2. It's a natural interpolation space between H1 and L2. It's just to say that there is a natural way to the... And then you get the fractional obstacle problem, which is the title of the talk, and I'm going to refer to it through this formulation again in this talk. So if you don't like the formulation, you can forget it. It's just that this exists. And then you can put more energies. You decide the energy you want to put, and the operator L from the previous slide is the Frechet derivative, or the first L2 variation of the corresponding energy. So the PDF formulation from before can be recovered from the energy looking at the Frechet derivative. So I gave you two formulations of the obstacle problem, if you want. One is the PDF formulation, two is the variational formulation. Let me go to a third one. In this case, I'm a bit more uncomfortable introducing it because I'm not an expert. So the obstacle problem, or the fractional obstacle problem, is very interesting from an application point of view, and the PDE community has gone into it in the last 20 years, in part thanks to the application side. And to be fair, the problem has been studied as much by analysts as it has been by probabilists. So what I want to do now is to give the probabilistic interpretation of what the obstacle problem is for them. For that, disclaimer, I'm not a probabilist. So I do this almost more for me than for you. You see. So just a couple of definitions first to introduce what I want to say. What I'm gonna define what the obstacle problem is for them. They call it the optimal stopping problem. In this setting, they call the optimal stopping problem to many things. This is one of them. So first, just start. I'm going to consider Levy processes. Levy processes are just memoryless stochastic processes. I guess everyone is comfortable with what a Brownian motion is. Levy process is just the natural generalization of Brownian motions when you remove the assumption that the paths are continuous. So you have a particle that is moving, and maybe it can jump. If you remove this assumption, you get Levy processes. But then the rest of assumptions of a Brownian motion are the same. So basically, I'm looking for a stochastic process with independent stationary increments. Just that it's a very general stochastic process and very natural to appear in nature. And given a Levy process, you can fully characterize, or let's say, let me call L, its infinitesimal generator, which is basically the operator that governs the evolution of a density of particles that are behaving according to a Levy process. For example, if the Levy process is the Brownian motion, L is going to be the Laplacian, and then you get the heat equation, which tells you how a density of particles is evolving if the particles are moving like the Brownian motion. No? Okay. So now that I gave the definitions, let's play a game. And this game is basically the obstacle problem. Suppose that you're given a payoff function, phi, that you know completely. Here I drew that payoff function in two views. So this is from top. So this is the ground. So this is in 3D, this is in 2D. You just have a payoff function that is, it has like this shape, it goes to 0 to infinity, but you completely know it. And you're given also one point, and you know that you're going to initialize with a particle that's going to be at that point, and it's going to move according to a Levy process that you also know. So you have full information. And we play a game. And the game is let the particle move. And you decide if you want to stop or not. And if you stop, you get paid the value of the payoff function there. Okay? So if you are greedy, you will want to maximize your benefits. No? So you see that this immediately tells you like you can only stop once, so this will immediately separate the space into two regions. There's going to be one region where you expect that it's going to be worth it for you to stop, and one region where you expect that you would like to wait and see what happens. For example, if the particle is very close to the top, often you would rather stop and get paid that than risk the particle going away and never coming back. If the particle is very far away, or is in a region where the payoff function is 0, why would you stop there? Just wait, because it's likely that it's going to go to a region with higher value. So, this is the game you want to play, and the function that maximizes the reward, and that tells you what you have to do, is basically the solution to the obstacle problem with this payoff function. This is called the optimal stopping problem in probability, and the solution to the obstacle problem with this obstacle is the value or the expected value of how much you will make if you play this game and you play optimally. So in particular, the contact set is going to define the region where you should stop. And the complement of the contact set is the region where you should wait. And you see, the region where you stop, you get your expected value, which is u, is going to be exactly the value of the payoff function, because if you stop there, you get paid that. But then everywhere else, if you don't have any reason to stop, the expected value has to be higher than the payoff function there. Otherwise, why would you continue? So this is the optimal stopping problem. And the formulation is exactly the same as the one of the obstacle problem. And in fact, if L is the infinitesimal generator associated to the Levy process that you know of, you recover the PD from before, so it's exactly the same problem. So just to introduce again what the fractional obstacle problem is if one imposes, or this is one case of the fractional obstacle problem, if one imposes that the stochastic process that you are considering is isotropic, or is invariant under rotations, then the only Levy processes that you can get are fractional powers of the Laplacian, which is the fractional Laplacian, which is an operator that I write here for the first time, and I will not write again. Okay? So this is a fractional Laplacian, which is the natural, if you want, in Fourier space, the natural definition of what the fractional Laplacian should be in terms of composition. It's an operator such that if you compose power 1/2 composed with power 1/2, you get the Laplacian. This is the fractional Laplacian. This is the definition. And if you have never seen it before, it can be a bit intimidating. But as I said, I'm not going to talk about it again. Just as a curiosity, this is a non-local operator. That means that the value of the fractional Laplacian of a function at one point depends on the value of the function at all points. Which is quite curious, because I told you that if you have this operator and you apply it twice, you recover with power 1/2, you recover the Laplacian, which is a local operator. But this is consistent. So this is a fractional obstacle problem. Again, when you put as Levy process the ones that are isotropic. Okay. So let me now introduce the Signorini problem. I don't do this for fun, you will see. So if I introduce yet another type of problem, it's because I want to relate them to what I did before. Just that you have to bear with me just for a second to introduce it. So the Signorini problem or thin obstacle problem is the same concept as before, except that now the obstacle, so it's like an obstacle problem, except that now the obstacle is degenerate in one direction, so it's concentrated in a set of codimension 1. But the concept is the same. You just take functions, if you want, that minimize the energy among all functions that are above, or whatever definition you want to do. You just, that the obstacle now is concentrated in a set of codimension 1. So if we are in Rn plus 1, the obstacle is in Rn. That's it. That's called the thin obstacle problem, because now the obstacle is thin. And if you want, this can be thought of as an obstacle problem in the degenerate case, and the PD is the same as before. We are looking for a function u that is above the obstacle, but now this condition only makes sense on the thin space. U is harmonic whenever it doesn't touch the obstacle. In particular, U is harmonic outside of the thin space, everywhere. And U in general is superharmonic. Just as a sanity check, if you think of L to be the Laplacian, again, or minus the Laplacian, this is well posed. Sets of codimension 1 have positive harmonic capacity, so we are putting an empty condition. If you put a set of codimension 2, sets of codimension 2 have 0 harmonic capacity, so this wouldn't make sense. So this only makes sense when you put a set of codimension 1. Okay? So if you put a Laplacian, at least this problem is well posed. And I will basically care about the Laplacian. So this is the Signorini problem. This is not just because. This is actually, if we are true to the natural flow of things, this was actually introduced as a problem before the obstacle problem, even if it seems like a generalization. And it was introduced in 1933 by Antonio Signorini in a slightly different setting, but I think it's interesting on its own, so I wrote it down just once. But he wanted to study basically elastic bodies. He had an elastic body, he put the elastic body on a table, and he wanted to study the region where the elastic body would touch the table. So a priori you don't know if the body moves, where's the region going to be. This is a thin obstacle problem because the table is like the obstacle, the elastic body lives in 3D, the table is 2D, so you want to understand that. The questions you may ask about this problem are the same as for the obstacle problem from before. Is what's the regularity of solutions, what's the regularity of contact set, and free boundaries. Now the free boundary is going to be a subset, so it's the boundary of a set in dimension n, in a space n minus n plus 1. But still, all the same questions as before make sense now. That's okay. In PDE, we sometimes ask ourselves, we have a solution to this in a domain, say omega. So this is a Dirichlet problem. You may try to ask yourself, what's the solution to this, or what's the solution? What's the regularity of the solution to an equation of this form if you assume that the boundary datum is smooth? No? So you have some domain, you put some smooth boundary datum, and you want to look at the harmonic extension inside, and you can wonder how smooth is going to be the solution to this problem up to the boundary according to the smoothness of G. For example, if G is infinity, we know that the solution to U, if the domain is smooth, say in a ball, the solution is going to be C infinity up to the boundary. Sometimes this is called the Dirichlet problem for the Laplacian. Sometimes we also ask about the Neumann problem for the Laplacian. So this is almost PD from the bachelor, I know that. Sometimes you ask about the Neumann problem, and you call it not G, but H. And now you wonder, if you have a solution to this, how smooth is going to be the solution? Right? So U nu is the normal derivative. And the answer is going to be the same. If U nu was smooth enough and everything is smooth enough, the solution is smooth enough. The seniority problem, the first time that it was formulated, was trying to understand a problem of this type, but instead of putting Dirichlet or Neumann conditions, the condition that was put was called ambiguous boundary conditions. And it was either U is greater than 0 and U nu is equal to 0. So either U is positive and then the normal derivative is 0, or U is equal to 0 and then U nu is more than 0. So U nu is the inner normal derivative. So you have two options. This is called ambiguous boundary conditions because I say either this or this. I didn't tell you what's happening where. This was used to model the problem I told you about before by Signorini. And this actually can be reformulated to this, just looking at one side of the problem. And we wonder now, for example, how smooth is going to be the solution. Because one could a priori think that, okay, all the conditions you are putting is 0, 0, everything is super smooth. So what do you expect? Why do you expect solutions to not be smooth? And now you will see. But yeah. The second question is, so there's going to be a region where the first condition is satisfied. There's going to be a region where the second condition is satisfied. And you don't know which region is what. This is precisely the contact set and the complement of the contact set here. So I can also wonder, a priori, if I don't say anything else, how smooth can these regions be? So, as I said, the thin obstacle problem is actually prior to the obstacle problem, even if it had been studied less. And it appears, as I said, in elasticity, but it also appears in fluid mechanics. It can be used to model, you have a cell, and you want to understand, you have a cell with a semi-permeable membrane, and you want to understand if liquid goes from inside to outside. So if it has a semi-permeable membrane, the liquid will only flow if there's enough osmotic pressure outside. This threshold of pressure is the thin obstacle, and there will be regions in the boundary of the cell where the liquid will flow because there's enough pressure, and enough pressure, and regions where it will not flow. This again is this model exactly. So the boundary of the cell is the thin space, the obstacle is the threshold pressure, and the diffusion is given by the corresponding operator. And the reason I'm introducing it, apart from its own interest, is that the seniority problem is actually, you see, I don't know what's the best way to explain that. Because you see the property I'm citing now, to people in analysis, is like a super well-known property. But I think it's only super well-known inside our world. And sometimes we assume too much here, and it's our fault. But basically the seniority problem, if you see what happens, basically the whole problem happens on the thin space. Because once you know what happens in the thin space, you can immediately know what happens everywhere just by taking the harmonic extension. And taking the harmonic extension is something that we always know how to do. So in reality, it's just a problem that happens in the thin space. So you could say, okay, then why don't you formulate the problem directly in the thin space? And I'm arguing in reverse to what people have done, but I'm trying to motivate it. It's because the seniority problem, what happens in the thin space, which is something that happens in Rn, is actually that you are trying to solve a non-local problem. Because now, if you have to go to the harmonic extension, what's happening here is going to be non-local. It cannot depend locally at each point. So what you are doing, really, on the thin space, is you are solving the obstacle problem for the fractional Laplacian of power 1/2. Okay, so I'm not proving it. This is basically called, this is a particular case, the easy case of the Caffarelli-Silvestri extension, which is a very well-known result in analysis, that basically tells you that you can express these fractional Laplacians or non-local operators as local operators if you are willing to go to one more dimension and just take a Neumann derivative, basically. For our community, this is a big deal. And actually, we just had a fantastic talk by David Lee about this topic precisely. And I think it's also curious, if you see you go to MathSciNet, you go to the most cited papers in the last 20 years, year by year, one of the top 5 papers is always called The Extension Problem for the Fractional Laplacian by Caffarelli-Silvestre. Well, it's this. It's what I'm trying to use here, just for mathematical curiosity. So, if I introduce this, it's because this allows me to study the problem from before, so the fractional obstacle problem, which is the problem that a priori I told you. Here you have a fractional Laplacian, which is an annoying operator, non-local, it's difficult to study. Allows you to study it from a local point of view, because now here, maybe I have a slightly more difficult problem, but the operators I can deal with are not fractional Laplacians of power 1/2, are just Laplacians. And Laplacians I know. Okay? So, to summarize, if you want to pick up again, it's a good point to pick up. So we have 2 unknowns. We have the solution U, and we have the contact set, which is part of the solution U, and in particular its free boundary. And then the questions are, what is the regularity of U, and what is the regularity of the free boundary? And none of these questions is trivial. For the classical case, one of them is relatively easy, but for the fractional case, none of these questions is trivial. Let me argue that they are not trivial, just with a small observation. You see, the optimal regularity, if you just think of the problem variationally, you could tell me, okay, you are minimizing an energy. Assume that it's a Dirichlet energy, or whatever you want to put, but something very small. You minimize an energy, and you are adding a constraint, but just put a constraint that is infinity. What could go wrong? You see, if there is no obstacle, and you minimize an energy, the Dirichlet energy, you get harmonic functions. Harmonic functions are analytic. How bad can it be? Adding a infinity obstacle. So you see, if you put an harmonic function and you do exactly that procedure, you're going to have a region where the function is going to have Laplacian 0, and then you're going to have a region where the function is going to have Laplacian equal to the Laplacian of the obstacle. Right? If you put an obstacle that is strictly concave, this Laplacian of the obstacle could be -1. So the Laplacian is going to go from 0 to -1, which immediately tells me that the function cannot be C2. So I can put anything I want, but the function is not going to be C2. And this is a strict property, in the sense that all solutions to the obstacle problem are not C2. You cannot have a solution that is C2. If you have a solution that is C2, it's because the obstacle was not there, or was not acting. Okay? So they are not C2. In the case of the classical case, that I'm not going to go into it, it's a bit easier. Solutions are actually C11, which means that second derivatives are not continuous, but they are bounded. In the fractional obstacle problem, the question is a bit more difficult. So, the second part is how smooth can the free boundary be? Even if I already know now, let's assume that I know that solutions are C1 or better. Still, the coincidence set between 2 C1 functions, even 2 infinity functions, the coincidence set, again, could be a fractal. So, how do I tackle that? No? So, a bit more of mathematical curiosities. The question of optimal regularity was first answered by Caffarelli and Silvestre, basically using the Caffarelli-Silvestre extension. If you allow me to be so bold as to say that Caffarelli very much probably had this in mind when doing the Caffarelli-Silvestre extension, had this application in mind. And basically they had the Caffarelli-Silvestre extension that allowed them to study the problem in a local setting instead of a non-local setting, and then try to apply techniques from a local setting, in this case the Algren frequency function, the Algren frequency formula. That is a formula that works for harmonic functions. They just said that, okay, if you have an harmonic function, maybe not an harmonic function, you just put a thin obstacle, doesn't change too much. We proved them, they had this regularity, this monotonicity formula, it worked. Just, again, for mathematical completeness, this took Caffarelli 25 years. Okay, so it's not. So Caffarelli studied this problem for the first time in 1979, and he proved that solutions to the thin obstacle problem were C1 alpha. But they didn't know how to get the optimal alpha. Then it was in 2007.
This was for S equals 1/2.
Yes. already for s equal 1/2, which is the easy case.
No, but before 2000, there was no calculation with s different from 1/2, right?
Or even 1/2.
No,
Well,
for 1/2 there was one.
1/2 there
Alberto
was
Calderon actually is responsible for introducing that technique of the extension.
No, the extension, yes. The extension, yes.
Okay.
Sorry. I mean
okay.
the regularity of the minimizer.
Yeah.
The extension, absolutely. Sure. No, I mean the problem of getting the optimal regularity of solutions to the thin obstacle problem is what took Caffarelli 25 years.
Yeah.
Not, because he first proved in 1979 that solutions to, so the minimizers from before were C1 alpha. C1 alpha means first derivatives are continuous with a Holder continuity exponent alpha, which is it's just an interpolation space if you want. Solutions are C1 alpha. To get the optimal regularity, which happens to be C1s, or in the case S1/2, which is the first they proof, is C1 1/2. So first derivatives are continuous with Holder exponent 1/2 and not better, is what took 25 years, between 1979 and 2004. And it was done thanks to the Caffarelli-Silvestre extension and the fact that they could apply monotonicity formulas. They didn't apply this first, but the fact that they could apply monotonicity formulas next. And the result said that answering the questions from before, like what's the regularity of the minimizer, what's the regularity of the free boundary, so the regularity of the solution to the thin obstacle problem or the fractional obstacle problem is C1s, and that's optimal. So you get C1s, you can produce examples, so it's C1s, S is the power. And then they had this result on the structure of the free boundary, which is a very deep result, but the first time you say it sounds tautological, which is the free boundary or the contact set, which just, so the contact set is going to be some subset of Rn, and its boundary is the free boundary, and they said the free boundary has two types of points. Those where the solution is regular and those where it's not. Then they tried to characterize it a bit more. Okay? But they said when u and phi, so phi is the obstacle, if you remember in the thin space. When u and phi are detaching from each other exactly at the 1 plus s rate, which is the rate given by the optimal regularity, I call those points regular points. And those are, so these are the regular points, and then they prove that every other point detaches, so the solution detaches from the obstacle at a rate that is 2 or higher. You see, 2 is larger than 1 plus s. S is between 0 and 1. 2 is higher than 1 plus s. So first they prove a gap, and then they prove two things. Either you have those regular points, which is where the solution and the obstacle are detaching at a rate 1 plus s, which is the one given by the optimal regularity, or these other points. And they call these regular points because then they prove that the set of points that satisfy this is an open subset of the free boundary, and the free boundary is C1 alpha in that subset, and a posteriori it's infinity. But then there's these other points that they didn't know what to say. Okay? Just as a comment, you see, this result is not, in analysis, is more typical. Logically, you are saying that the points that have the least regularity are the most regular ones. Okay? And then there's the points that have more regularity because at those points the solution is C2 or higher. At those points you cannot say anything. Okay? So this is like the implicit function theorem. If you have that the gradient is strictly positive, you can say things. But this is like the gradient is 0, then you cannot say anything. You can say things about the... Okay. So, maybe it's worth it for me to give a short overview on how do you prove this type of result, because I think it's interesting, the idea. It's not necessarily easy to follow the steps, but the idea is interesting because here Caffarelli was very much inspired by what people do in minimal surfaces, which is something that maybe some of you are more familiar with, and it's the following. So if you have a minimizing minimal surface, you may want to prove whether it's regular or not. And the procedure is now a bit standard. How do you prove if a minimizing minimal surface is smooth? You take a point in the surface, and you do what's called the blow-up, which basically means you start looking closer and closer to that point. You do a blow-up, and what you hope is that this is converging to some solution globally defined. What happens is that you have a monotonicity formula that tells you that this solution that is globally defined is going to be one homogeneous. So you study global one homogeneous solutions to a minimal surface equation, or minimizing globally one homogeneous solutions. And then you reduce your problem from before to classifying this type of minimizers. If you can prove, then there's another theorem that's called an improvement of flatness theorem that tells you that if all the solutions that you obtain with this procedure are planes, which means roughly that the function was C1 there, then your solution was smooth to begin with. So basically what you do is you take one point, you do a blow up, and you reduce to the one homogeneous solutions, and then you hope to be able to classify one homogeneous solutions. And if you can classify one homogeneous solutions to be planes only, then you can say that they are smooth. This is the strategy of minimal surfaces. This is what they do. Basically, they do the same thing. You take your function with your solution to the obstacle problem. You have the obstacle. You just take your function, you subtract the obstacle, and you do a blow up. What does it mean to do a blow up? It means looking at the function at smaller scales. So, I don't know what the best way to write it, but so this is your domain, this is your free boundary. You just take a point in the free boundary, and you look at the function at smaller and smaller scales, and you keep zooming in. You keep zooming in, and you hope for the best. And basically, you keep zooming in, and thanks to the algorithm frequency function, it tells you that if you keep doing that, in the end, you're going to get a global solution that is going to be homogeneous. The difference with minimal surfaces is that I can only say that they are homogeneous. I can only say which homogeneity they have. So what they did is they took the free boundary, they did that at every point in the free boundary, and they said, okay, now every point of the free boundary, if I do a blow up, I'm going to get one number. And that number is the homogeneity at that point. What does this mean? It means that if you have a set, you have a contact set, you have a free boundary, at each point, it tells you at which rate is your solution separating from your obstacle. Rate, it means at which power. And the power from before we saw it was either 1 plus s or something that is greater than 2. They just did it for me. So you have one number associated to each point in the free boundary that you want to use to understand what the free boundary looks like. And they prove that this number is either 1 plus s or some number between 2 and infinity. Both included. So basically you have a gap, is what they did. And then they said, okay, let me look at the points that the number is 1 plus s. They prove that this is an open set because the frequency function is lower semi-continuous. And then let me classify solutions that are 1 plus s homogeneous. Then they said all solutions that are 1 plus s homogeneous to this procedure are things that are going to look like that. It's like hyperplane. You get 0 and then growth like 1 plus s in some direction. So basically, if you think of this as a solution to the obstacle problem, the free boundary is just a hyperplane. So these solutions have smooth free boundaries. So you take these solutions, you get that type of blow up, which tells you how the solution looks locally at this point. And if locally you look like that, you need another theorem that tells you that, okay, if you had to look like that very close by, it means that you are actually looking like that around. This is another improvement of flatness type of theorem. And this is a black box now, but this is a type of result. And then there's the other question, which is, okay, so now this means I fully understand these points. There's those points where the frequency is 1 plus s. At those points, the free boundary is going to be C1 alpha, a posteriori is going to be C infinity. What happens when the frequency is between 2 and infinity? And this is much less known. So there's nothing that I can, I will be much more thorough now, but this is much more open. So what's happening here? And just let me finish that this is not the typical way it was originally done. Just that if you want to recover the optimal regularity, you can do it now. You didn't need to know the optimal regularity to do all that. Originally, it was done in the reverse way, but you can do all that and then recover the optimal regularity. Okay, so again, it's another point to pick up. We have the fractional obstacle problem, which is this, but I said that it's not so important to know what it is, but basically functions above the obstacle. They are S harmonic whenever they don't touch the obstacle, but in general they are S superharmonic. And now we have a free boundary that is divided according to the frequency of points. What I want to understand in the end is what shape can the free boundary have. And I said there's going to be those points where the free boundary is going to look. So if you think of this as the contact set in Rn, there's going to be those points where the free boundary looks like regular points, where the blow-up looks like a half-space solution. And then there's going to be a bunch of other points that I don't know nothing about. So, for example, the blow-up could be like a paraboloid like that, but it could be other weird things. Right? What I want to understand is what shape of points can I have at the free boundary? And this is, in the classical case, this is much easier, just to say. In the classical case, you can only have two behaviors, and it's very specific what you can have. The good thing about, or bad thing, if you want, of the fractional case, is that the types of behaviors basically depends on the types of frequencies you can have. And since you can have infinitely many frequencies, you can have infinitely many behaviors. So, but at large scale, the free boundary can be divided into 6 types of points. And what I'm going to attempt is to bother you, or to bore you for 1 second with the points to tell you what could go wrong, or on what we know and what we don't, because I think also the open questions are interesting here. And hopefully then it motivates the result I want to introduce. So, you have the 6 points. The first set of points is the set of regular points that I said before, is the set of points that have frequency 1 plus s. And this is the set in dimension n. The boundary of a set in dimension n is n minus 1 dimensional, in general, if the set is nice. And these are C infinity n minus 1 dimensional set. Good. These are the good points, these are the ones I like. If every point was like that, I would be very happy. You have a picture, this is a possible contact set. Regular points are like these points. Okay? Then you have singular points, which are those points with even frequency, so 2, 4, 6, etc. For them, we know that they are n minus 1 dimensional again, and they are those that have 0 density. So in this picture, it would be like this. This is a 0 density point. The contact set has 0 density around that point. This is a possible singular point. It's called singular point. This doesn't mean that it's not regular. Singular points are a subset of non-regular points. It's a particular case of non-regular point. But this could happen. The good thing about them is that we know that they are contained in unions of smooth manifolds. So they are bad, but we kind of expect them, but they are not too bad. Then we have, I call them gamma odd. As far as I know, people have not given a name to that. Gamma odd points. They are those with frequency, it says 2m plus 2s. If you think of S1 half, which is the case I'm more comfortable with, which is the thin obstacle problem as I stated it before, S1 half, these are odd frequency points. That's why I call them gamma odd. So it's odd frequency starting from 3, so 3, 5, 7. And they are those points that have full density. So for example, this could be an odd frequency point. And they can be a priori n minus 1 dimensional again. And more interestingly, we don't know if they exist. So we know that if they exist, they are going to have these properties. But nobody has been able to produce one example of one of those points. Okay? So this is how they should look like if they exist. Then you have gamma half points, which are points with frequency 2m plus 1 plus s. So it's, if you think again s 3 halves, this is an even number plus 3 halves. It's basically regular points plus an even number. It's like a regular point plus a single point, if you want. They are n minus 1 dimensional again. And a priori, we don't know if we can distinguish them from regular points. We know that they can behave like a regular point completely, so this could be a line of these points that are not regular, but we don't know if they are necessarily regular. And then we have gamma star points, which is the remaining frequencies, the ones that I didn't say here before. And I say remaining because the good thing is that they are at most n minus 2 dimensional, so they are smaller than regular points. And the bad thing is that we don't know if they exist again. But if they exist, they should be something like that. Okay, so here the free boundary is one-dimensional. This is a zero-dimensional point. So if they exist, they could be something like that. It could be a gamma star point. We don't know if they exist. The good thing is that at least those points, we know that they are small. So at least we can say that the free boundary, okay, most of the free boundary is not going to be this. These are one dimension less than the others. And then you have the most annoying points of them all, which are gamma infinity, which are those points of infinite frequency. So I said remaining, but I didn't mean infinity. Those points with infinite frequency, that they are basically, they are obtained. You see, this is a solution to the obstacle problem. You have the obstacle, you have your solution. Now, once you have this, take the obstacle and modify it like that. And modify it infinitely, but make it the ugliest thing possible, touching the solution, but not pushing the solution, just touching. Then the solution to the obstacle problem is going to be the same, but now the contact set is going to be horrible. So these are a bit artificial solutions. You can basically make anything you want with that. So you can make this. Yeah? This is possible. This for sure you can do. Okay? So these points are annoying, and they can have, these are free boundary points, and as free boundary points of a set of dimension n, they can have dimension up to n. So they are very annoying. Okay? So you see, the setting is a bit weird, because I wanted to study free boundary points, and my conclusion has been, okay, there's those regular points, which are very nice, and then I threw at you a bunch of other points that are not so nice and for which I cannot say a lot. And the most annoying part, if you want, is that many of them have the same size as regular points. So I could have a free boundary, I could give you a solution to the obstacle problem, I could have a free boundary that is entirely made of points that I can say nothing about. Which is not a very satisfactory result, no? But this is possible. This, I can produce it. So there's nothing we can do about it. And this is where I wanted to present one of our results, which was basically, I would like to say in some way that regular points are better than that. Or that they are more common than the other points. From what I can say now, regular points have the same size as everything else. But if I can say that things are smooth at regular points, I would like to say that, okay, this in a way is the typical behavior of a free boundary. I don't want to have a setting in which I have information in a subset that says nothing. And this is the result. What we do is the generic regularity of free boundaries, which is, I want to say that for almost every solution to the obstacle problem, things are nicer than that. So first I have to define what it means for almost every solution. And we do this generic type property, which is called generic in the measure theoretic sense. This is part of something called the theory of prevalence, which is not very well known even among analysts. And basically what we do is, okay, so you have a solution. Solutions to the obstacle problem are given by the free boundary. Right? I'm sorry, by the fixed boundary. You put a boundary datum and you get the solution inside. So what we do is, okay, if I perturb a bit the value in the fixed boundary, do I get better regularity properties just by perturbing a bit? And what we do is you just take a free boundary, you have your problem, you put your free boundary condition G, and now you consider G plus lambda. You can put other things, but G plus the number lambda. So G is increasing by lambda or decreasing by lambda. And then you have a family of solutions, U lambda, indexed by this lambda. And we say that a property holds for almost every solution if it holds for almost every lambda. Which in particular means that it holds for arbitrary closed solutions if you take G just a tiny bit small, a tiny bit bigger or smaller. And this is a result from 2021, which I wrote on, where we prove that the set of points that are not regular, before I told you it could be n-1 or even n-dimensional, are actually n-2 dimensional generically. So for almost every solution, most of your free boundary is going to consist only of regular points. So the free boundary is going to be C infinity up to an n-2 dimensional set. It's going to be a set. Remember, the free boundary is an n-1 dimensional set. So I'm saying that it's C infinity up to a codimension 1 set on the free boundary. So regular points are better in a way because they are the typical behavior, and saying something about them means saying something about the problem. The second part that I can say very fast is that in the case of infinite frequency points I said before, so the very annoying points, these ones that I told you that can have dimension up to n, we not only prove that they are generically smaller, we prove that for almost every solution, they don't exist at all. And it's not only for almost every solution, it's that the set of solutions for which they exist has Minkowski dimension 0, which is almost counted. So they are very, very, very rare. So basically it means that if you see that, someone gave you the solution to produce that. It's a way to say that you only see that if someone is actually doing it on purpose. Okay? Or in that setting, I told you have the obstacle, you modify the obstacle specifically to get that behavior. But as soon as you move it a bit, this disappears. And then, more recently, so this solution tells you that it's n-2 dimensional. If you want, it says that in dimension 1, which is not very useful here, but in dimension 1, generically, there's only regular points. Almost every solution has only regular points. And more recently, with Clara Torres La Torre, we could prove that if you consider S1/2, so the fraction of the thin obstacle problem, in that case, or the fractional fraction with power 1/2, in that case, you not only prove that generically in one dimension you have no regular points, you can prove it up to 3 dimensions. So you can gain 2 extra dimensions and prove that generically up to R3 in the obstacle case or R4 in the thin obstacle case, the free boundary is fully made of regular points. So there's no other point that is not regular. So in particular, the free boundary is the C-infinity manifold.
And this is generically with respect to monotone families.
Yes. Well, yes, absolutely. There's other definitions of genericity that say that you can say something is generic if you can find a small perturbation where it happens. And yes, so this is everything I wanted to say. Thank you.